This video is not about the theory and mathematics of Fourier transforms and sine waves. You can look that up. There is plenty of stuff. In this video, I do try to show the concepts and uses of Fourier transforms and sine waves. What is a sine wave? There is one sine wave below. Amplitude is measured in the vertical direction. Frequency is measured in the horizontal direction. Sine waves repeat infinitely. One repeat is a cycle. Frequency is the number of cycles per second. Assuming the horizontal direction is time. Cycles per second is also called hertz. The two sine waves below have the same frequency and amplitude, but their alignment is different. This is called a phase difference. The top sine wave has lower frequency. The bottom sine wave has higher frequency. When speaking about sine waves, low and high refer to frequency, not amplitude. Why transform? Which is correct? 3.2 or 5.2 minus 3 plus 1? That's right, they are the same thing. Remember that. There are three sine waves below. Adding those three sine waves gives the bottom shape. The sum of these three values is the bottom value. And the sum of these three values is the bottom value. And the sum of these three values is the bottom value. So the three sine waves are the same as the bottom. Just like when we noted that 3.2 is 5.2 minus 3 plus 1. Okay, so what? Joseph Fourier showed that summing any amount of sine waves of different frequencies or different amplitudes or different alignments makes exactly one shape. The bottom shape is only produced by exactly those three frequencies, amplitudes, and phases. No other sine wave combination makes that shape. Some other properties of sine waves. 1. A sine wave frequency cannot be made by summing other sine wave frequencies. 2. Sine wave frequencies do not affect each other. Additionally, Fourier also figured out how to start from a shape and derive the sine waves that add up to it. That is called a Fourier transform. Proving Fourier stuff requires some calculus. I'm not going there. You can look it up. A Fourier transform takes a shape and determines the individual sine waves that add up to that shape. Why is that useful? For music or speech or any other sounds, the amplitude of the sound wave makes a shape. In electric circuits, the amplitude of the voltage makes a shape, and the amplitude of the current makes a shape. When you pass a sound or electrical shape through simple objects, that shape gets distorted, unless that shape is a sine wave. The shape of sine waves is not distorted. The amplitude and phase of sine waves are changed, but not their shape or frequency. For instance, sound sine waves interacting with walls or windows retain their shape. The amplitude and the phase alignment will be changed, but it will still be the same frequency and shape.
Consider a sine wave going through this wall. The amplitude of a high-frequency sine wave will be decreased more than the amplitude of a low-frequency sine wave. Now, why the amplitude of high-frequency sine waves is decreased more than the amplitude of low-frequency sine waves is complicated, but they are. Now, performing a Fourier transform on this side of the wall and on the other side of the wall allows us to compare how much the frequency amplitudes are decreased from one side to the other for each sine wave. A filter can then be designed which will boost up the amplitudes on the other side of the wall to compensate for the effect of the wall, if you want to. But you can, of course, use that same information to compute a filter which will take a sound on this side and simply change it to what it would sound like on the other side of the wall, even though there's no actual wall here. So of course you can change the sound that's coming right here to make it sound like a wall exists even when one doesn't. That's the kind of thing that's useful in Hollywood. Now, a similar example to that is when you have, say, a music venue or a theater, and you're getting reverberations off the walls and you actually want to get rid of them, or at least you want to understand how they're being caused, and therefore you can reduce them. So again, Fourier transforms come into great use in that kind of situation. Now, beyond just the amplitude of every frequency, a Fourier transform will give you the phase of every frequency. The phase is, of course, the alignment, okay? As a sound wave comes in this side and hits it, it then penetrates the wood and comes out on the other side. Now we know there's going to be an amplitude change of that sine wave. And there's also a phase change because there is a change in the timing as it gets through here. Now you might think that there would be a delay going through this, but that's incorrect. Speed of sound in air is about 343 meters per second. The speed of sound in wood is about 4,000 meters per second, so 12 times faster-ish. That means that a wave that comes in is actually coming out faster than it would have without the block of wood in the way. Now on the other side of the block of wood, the amplitude of the sine wave is going to be decreased. Now if we perform a Fourier transform on the sound on the other side of the block of wood, we can find that amplitude. The speed of sound in air is slower than the speed of sound in wood. So the sine wave is actually coming out shifted relative to where it would have been if it just continued through the air without the block of wood in the way. If you perform a Fourier transform on this side of the block, it won't tell you how many full cycles of the frequency it took to get through the block. So it might take, say, 3.2 cycles or 4.2. It'll only tell you the 0.2 part, that is the fraction of one cycle misalignment between where the sine wave is now and where it would have been without the block in the way. So it can't tell you that it's, full cycles mean nothing. It can only tell you the fraction. That's what the phase is. It's only between 0 and 360 degrees. So it cannot tell you kind of the full time delay just from a Fourier transform. Okay, this actually causes lots of trouble in various, for instance, seismic data processing. This is kind of a big issue. Now, this phase issue comes up all over the place in seismic data processing. For instance, for deconvolution, you usually have to make a minimum phase assumption. This also comes up in dispersion, which is caused by the fact that high frequencies travel slightly faster than low frequencies. And so the phase alignment gets changed, and a Fourier transform can't really tell you how much, just exactly whether it's changed by an entire loop and some, or just some. Similar issue is with inverse Q processing, where it is difficult to analyze and tell what the phases of the frequencies are. And the same kind of issue comes up in matching pursuit Fourier interpolation using priors. Just to name drop a few things there.
Electrical sine waves interacting with capacitors or inductors, coils, retain their shape. The amplitude and the phase alignment will be changed, but it will still be the same frequency and shape.
Now, within capacitors and inductors, the voltage and current have a complicated relationship. You can look that up. We're not going to go into it here. But sine waves going into these things come out as sine waves. They have the same shape and the same frequency, only their amplitude and their phase is changed.
That makes Fourier transforms very useful. Once we know what the object is going to do to the amplitude and phase of individual sine waves, we can compute how that object is going to change any shape that passes through it. 1. Use a Fourier transform to get all the individual sine waves of an input shape. Generally, this step is called going to the frequency domain. 2. Apply the amplitude and phase changes of the object to the individual sine waves. 3. Add up all those changed individual sine waves and get the output shape. Generally, this step is called going back to the time domain. Now, instead of step 2, we could also just apply whatever amplitude and phase changes we want to the individual sine waves. Generally, this is called filtering. Low-pass filtering, high-pass filtering, band-pass filtering, and so on. There are various ways to design, construct, and apply filters. I don't discuss that herein. Why sine waves? Why not use square waves or other waveforms? If you use a program like Audacity, you can generate square waves. Filter those square waves and they will distort, but sine waves will not distort. So, is that why we use sine waves? Nope. That is backwards. Audacity filters are specifically designed not to distort sine waves. Filters could be designed not to distort square waves. Some philosophy about sine waves. I bet you didn't see that coming. Ultimately, we use sine waves because many simple things seem to prefer them. For sound, sine waves interacting with simple objects remain sine waves afterwards. For electricity, sine waves interacting with simple components remain sine waves afterwards. You might say that basic physical processes prefer nice, smooth changes. And sine waves have exactly the right amount of smoothness to get through those processes without distortion. Okay, that's a fuzzy explanation, but if you know the physics and mathematics, you don't need this video. A bit of irony. Most people's familiarity with waves comes from looking at oceans or lakes. Fourier transforms might be wrong for those waves. In the details of Fourier transform theory, it says that the shapes must be mathematical functions. Some ocean or lake waves are not functions. This breaking wave shape cannot be Fourier transformed. This shape is not a function. It has more than one value at some locations. This wave shape also appears on ocean and lake surfaces. This is also not a function because it has more than one value at the same location and time. An important thing to note is that the waves on the surface of oceans or lakes are not sound waves. Those are surface waves. Sound is a pressure wave. Sound and other pressure only has one value at any location and time. Electric voltage only has one value at any location and time. Electric current only has one value at any location and time. So Fourier transforms have no trouble with those cases. But Fourier cannot surf. No shooting the curl for Fourier. Consider the shape below. A Fourier transform will derive the sine waves that can be summed to produce this shape. But that does not mean that any sine waves actually existed. It is purely mathematical. Sine waves are just another representation of the shape. Using the plot spectrum option of Audacity, the shape has 4 sine waves with large amplitudes. The 4 sine waves that can be summed to the shape. Sometimes it is easy to believe that a shape was created by sine waves, and so Fourier transforms cause no philosophical or conceptual difficulty. This is particularly true for music, since many instruments make vibrations, and vibrations look a lot like sine waves. But other times a shape is created by processes that have nothing to do with waves. Yet Fourier transforms can still be used. Consider this shape. A Fourier transform will allow you to determine which frequencies are noise, and then you can filter them out. After filtering carefully, you see this shape, which is a fuel injector waveform. This is the off voltage level, battery positive. This is the on voltage level, battery negative. This voltage is induced by a magnetic field collapse. This voltage is clipped off due to a Zener diode. This voltage is a Pintle hump, which is induced by the motion of a metallic object in a magnetic field. None of those processes involve sine waves, but a Fourier transform does not care. You can still use it with this shape. You may hear Fourier transforms referred to as DFT or FFT, which stand for discrete Fourier transform, fast Fourier transform. Discrete Fourier transform means it is used with sampled values, such as digital sound recordings. Fast Fourier transform is just a rearrangement of math to speed up discrete Fourier transforms. You may also hear that Fourier stuff is easier using complex numbers, which are combinations of real and imaginary numbers. You might think complex numbers makes everything more complicated. But Fourier stuff quickly gets into calculus and is actually simplified using complex numbers. Think of it as pulling some of the complexity out of the mathematics and shoving it into the numbers. The only detail I want to say about complex numbers is that the real part is not amplitude, and the imaginary part is not phase. You need to perform a small trigonometric computation to get amplitude and phase from a complex number. Some other noteworthy Fourier and sine stuff. This is a triangle wave, and the amplitudes of the sine waves that sum up to it. Now, apply a filter which reduces the amplitudes of the higher frequency sine waves, as plotted below. The triangle wave after the amplitudes of the higher frequencies have been reduced. Note that the sharp bends in the triangle wave have been rounded off. Reducing the high frequency sines results in smoothing the rapid changes in shape. This is reasonable since sine waves are smooth. So, sharp bends must be made of higher frequencies. But saying sharp bends are made of higher frequencies is misleading since each sine wave exists across the entire shape, not just near sharp bends. Better to say, sharp bends are made of higher frequencies with phases that are precisely aligned relative to each other. This is a spike. Mathematically, the Fourier transform of an infinitely thin spike contains all sine wave frequencies. Here is the spectrum of the previous realistic spike. After passing that realistic sound spike through a wall or passing that realistic electric spike through some component, we get this distorted spike. A Fourier transform of the distorted spike produces the spectrum below. So we can design a filter to reverse or compensate for some or all of the effects. This is why inputting a spike is so useful. We do not have to input the sine wave separately to see what effects occur. The spike is enough. Lastly, I've heard the question, at what frequency do sound waves turn into electric waves? The answer is that sound and electricity are different things. Sound never turns into electricity. A microphone inputs a shape in sound and creates the same shape in electricity. A speaker inputs a shape in electricity and creates the same shape in sound.